So today we begin lecture 62, the second part of the two-part lecture on real coded genetic algorithms. And this is part of my optimization series, and I am Dr. Ranjan Ganguly. Now we see that there are a whole bunch of similarities between binary GA and real coded GA in terms of the development of the starting population, the creation of the mating pool. The primary difference is that whereas in binary GA we are using bit based coding, here we are using floating number based coding. Now we discuss how we are going to exchange the genetic information between two parents. So this crossing which we have to do in real GA is different from binary GA, and we will see why this is so. So if we wanted to extend the simple concept of binary GA, we could do something like this. We could take two sites within the parent design vector as the crossing site and then exchange the variables inside the two crossover sites. For example, I could take two 6 variable parents given here by father and mother. Now for each of these we have added a subscript F to denote father, and we have put a subscript M to denote mother here, and there are 6 parts of this vector. Now what we could do is, if we followed the same mindset as we had in binary GA, we could take two crossing sites randomly and maybe we got 1 and 3. So at that point we put these vertical lines at location 1 and location 3, taking from the right hand side, and then we would exchange the information which is present in this site. So for example, here the father variables xf4 and xf5 have moved from the father vector to the child, and the child information has gone to the mother. So this swapping has taken place. But one of the things we see here is that unlike in the case of binary GA, where that would essentially lead to change in several design variables and creation of completely new points, here this information is simply being shifted here, so this coordinate is not getting changed. So this strategy which we outlined just now works well in binary GA when the variables are coded strings. But in real coded GA, a simple swapping of design variable would not introduce a new point. Essentially, you still have that same point xf4 and xm4 which you had before. So they have just been shuffled, but these are not necessarily very good points to discover new parts of the design space. So we need a method to create new design variables which is unique to this real coded GA and the use of floating point numbers. So the first type of crossing which is done here is known as the blending method. And in the blending method we define the two children using these equations given here. So here they are, you have the father and the mother points given again by the subscripts F and M, and then what we do to combine this mother and father, we use this value beta here, beta and 1 minus beta, and so essentially we are blending this point here with this point by using this beta value. Now let us explore what happens with different values of beta here. Now again, to summarize, xmn is the nth design variable in the mother design vector, and xfn is the number nth design variable in the father design vector. And so these are being blended using this value beta, and beta is a number between 0 and 1. Now if we look at the limiting cases when beta is 0, then x nu 1 would simply become xfn and x nu 2 would become xmn. When beta is 1, x nu 1 would become xmn and x nu 2 would become xfn. So these are the two limiting cases, and in these cases you see that the child essentially becomes a clone of the mother or father situation. So the interesting cases are going to be when beta is somewhere between 0 and 1 and not at the ends. If beta is 0.5, you can do the calculation and you can find that the two children are the mean value of the two parent design variables. So that's also a reasonable choice in some cases. But the best results you will get if you use a random number beta between 0 and 1, typically a uniform random number, and take the values of two children. So we see that this blending crossover method combines information from both parents to get the children, and therefore it simulates nature, because that's what happens in nature, is that aspects present in both parents are passed on to the children, and this is done randomly. So if a couple has several children, you will see that each of those children are basically unique, but their genetic material does come from those parents. So the blending method, what it does is it interpolates between the parent values. And a negative part about this is that it does not go out of the range which is prescribed by the parent value, so you do not have extrapolation into the design space. So there are some ways to create children which are extrapolated into the design space, and one of the methods is known as linear crossing, where you can create three children using two parents. So here you can see these three children are created, which are denoted by x nu 1, 2 and 3. And so here you use 0.5 in one case, you use 1.5 minus 0.5 in another case, and minus 0.5 and 1.5 in one more case as the weighting constants to create these particular new variables in terms of children. So one of the things which can happen when you do this extrapolation is sometimes the child can go outside the bounds of the design variable. So again, recall, if our design variable bound was 0 to 10, you may get a child which is beyond 0 to 10, maybe 15 or 20. So in that case, you need not select that particular child to continue in the next generation. So essentially, one of the strategies which is recommended in linear crossing is that the two best children which come out of the three are selected for further study. So here you have these three children here. So just to give you an actual example of this situation, you could have the xmn to be 1, xfn to be 2. So if I plug in these values here, for example, I get here 0.5 plus 1, that is 1.5. The second value is 0.5. The third value is 2.5. So this is how I can get three values here. Now the advantage of linear crossing is that it both works within the domain of the parent values, and there is a possibility of it getting out of this particular domain, leading you to expand your search outside the particular band which you are in. Now, one of the things you can immediately see by looking at the current definition of linear crossing is that it is deterministic. So we can introduce a further generalization of this concept by creating some randomness, because in some cases you may have to create more than three children, because there may be a case where more than one need to be removed because they lie outside the move limits of the design variable. That of course depends on your move limits. So this method is known as the heuristic crossover, and here we have again two parents defined by the mother and father variables, xmn being mother, xfn being father, and then we use this beta here, which is now a random number. So this heuristic crossing will let you generate children both inside and outside the parent range. And depending on the value of the random number beta between 0 and 1, you can get a plethora of points which you can use to solve this problem. So heuristic crossing also introduces randomness, which was not present in the linear crossing, which we discussed before. So that is again always good whenever you are dealing with stochastic optimization methods, is that you should take advantage of randomness during the definition processes. To implement this two-point heuristic crossing, let us consider two parent design vectors. So these are the father and mother. So the first is, for example, 2.762, 4.384, 1.236, 0.524, and similarly for the mother vector. Now let us say that each design variable has a bound of 0 to 10 as the lower limit and the higher bound. Now let's use a random number generator, pick two crossing sites as 2 and 3. Now create three random numbers. We get these three random numbers here, and then using the heuristic crossing formula, we obtain three children here. So here you can see I have used this beta value as the first random number, 0.1783. The second one is 0.8264. That's the second random number. And the third random number is 0.3123. These are of course the father mother strings and the father string and so on, and I get three values here. Now immediately you see that two of the values lie within the design space as defined by the move limits, but the third value is outside the design space. So this child which is outside the move limit of the design variable is not selected. Now we take the two values which we obtained before and we perform the crossing between those 2 points we discussed before, 2 and 3. So essentially we put these values here. Now these two values are completely new. They are very useful in terms of proceeding forward, and again because of the use of randomness at different points of time and depending on how many times you run this particular GA, you are going to get new points. So this 2-point heuristic crossover is a good way to work with real coded GA problems, and generally it is the method which is recommended as far as practical applications are concerned. Now we have to look at the next biologically inspired method by which we move around into the population. So again, like we discussed before, mutation is needed in real GA to ensure that the method does not get stuck or converge to a local minimum point. And we apply mutation with the probability P subscript M. So we need to change n into PM design variables in a random manner. So recall that small n into capital N is the total number of real numbers in the population, small n being the size of each design vector and capital N being the number of members in the population. So when you multiply this by the mutation probability, that gives you the number of design variables which need to be changed. So let us consider design vectors of size n is 6 and capital N is 10. And this is the population. So in that case, if the mutation probability is PM is 0.05, we have to change 6 into 10 into 0.05 equals 3 design variables in the population. So that's the number of design variables which we change, and again we change them randomly. So we randomly select three variables from the population, replace them by a random number which lies between the move limits corresponding to these variables. And again, you know how to select a random number, so you select a uniform random number between 0 and 10 if you are working on that problem, and simply put these random values there. Now, when should you use binary GA and when should you use real GA? Now, what I would suggest is that problems involving a low-level discretization are better solved using binary GA, though your variables may be real, because there are many situations where you do not really need to discretize the design space to a very high level, and in those cases, binary GA may be good. But if you want your solution to a very high level of correctness in terms of the decimals, you want floating point number representation of your design variable, then it is better to use real coded GA in terms of storage requirements. Now, recent literature typically shows a growing popularity of real coded GA compared to binary GA, especially for different design optimization problems where the variables tend to be floating point numbers, such as expressed in centimeters or newtons or pascals, as the case may be. So now this was just a brief introduction I have given to genetic algorithm. This is a pretty vast topic. There are books devoted to this topic, which you can see. The best book is probably Goldberg. That is the seminal book in this field, though it may be somewhat dated, but you can see the progress of some of these concepts by looking at Goldberg's book and then looking at some of the books which came up later, such as Mitchell and Haupt, and also Dave's book on optimization. Now, GA is a way to solve multi-objective problems, and there are very powerful methods for multi-objective optimization, which is probably beyond the scope of this class. But again, there is a book by Dave in 2005 you can consult for that information, and he has developed a program NSGA2, which you can also freely download from the web and use if you are doing multi-objective optimization problem.